All right, so in this video, we're going to be looking at two separate theorems. One is the rational zeros theorem, and the second is Descartes' rule of signs, in order to help us factor larger polynomials that are not obviously able to be factored from their current standpoint. So we want to be able to guess some likely values, our best guesses for possible things that the zeros could be if they're rational. And then the rule of signs will help us determine maybe whether we should start with the positive numbers or start with the negative numbers in terms of whether we have potentially more or fewer positive zeros or the negative zeros, just to help us kind of narrow down our list of values that we're going to need to check. Because really the only way that you can factor problems like this when they're not in factored form and it's not obvious how you could factor them. This is 5 terms for both of these examples. If we had 6 terms, maybe we could use like an even number of terms. Maybe we could use factoring by grouping, although that's not at all guaranteed. So how do we approach this? Well, we have to do division, basically. We have to pick some zeros, pick some potential factors, divide them out, see if they work, and then go from there. And so we don't want to check every possible value. We want to try to, again, strategically think carefully through what values should I be checking, what values are possible. And then if you exhaust all of those values, then you know that you really only have irrational zeros. They might be positive or negative, but at least you can eliminate all the rational ones through division. All right, so we're going to start with the rational zeros theorem. And basically the rational zeros theorem says that in sort of abstract terms, the factors of the leading coefficient and the final constant determine the possible rational zeros. So let's consider a specific example, 3x minus 5. If that's a factor of our polynomial, the 3 is a factor of whatever the leading coefficient is if you FOIL everything out, and 5 is a factor of the final constant after you factor everything out. We would set this factor equal to 0, and when we solve it, notice what's going to happen. We're going to put the 5 on the other side first, and then divide by the factor in front of x. So this is the general format we're following. So the possible rational zeros are of the form q plus and minus q divided by p, where p are the factors of the leading coefficient and q are the factors of the final constant. Now, I will just note briefly that if you don't have a final constant, that means there's an x on every term, assuming you put it in descending order, and then factor out that extra x, so however many x's you need, and then the resulting one can be applied to this. The resulting factor with a constant can be applied to that. All right, so let's look at our first example. The final constant is 24. And so the possible factors, the plus and minus, we're going to leave in the expression. So the possible factors of 24 for that final constant are 1, 2, 3, 4, 6, 12, and 24. And the leading coefficient factors are 1 and 3. So the possible rational zeros are going to be 1 plus and minus 1, plus and minus 2, plus and minus 3. So in each case, we're dividing each one of the constant factors by 1, 4, plus and minus 6, plus and minus 12, plus and minus 24. But now we also have to divide all of those by 3. So plus and minus 1/3, plus and minus 2/3. Now, if I divide 3 by 3, I get 1, which is already on the list, so we'll skip that. 4/3. 6 divided by 3 is 2, that's already on the list. 12 divided by 3 is 4, that's already on the list. 24 divided by 3 is 8. That was not on the list. So these are all the possible rational zeros for our first example. And again, this is a lot, but it's less than everything. So we know we don't have to test things like halves or quarters or fifths or sixths. We have a couple of thirds to check. We have a couple of whole numbers, but we know we don't have to check 5 or 7 or 10 or things like that. We have only these ones as possibilities. Some of these will either work or all of the zeros will be irrational. Now, in a textbook problem, you would expect at least some of them to work. And as a personal strategy, I would recommend starting generally with the whole numbers that are closest to 0, and then work from there, work outward, and then work to the sort of more complex ones that you might have to evaluate. Once you find one, then your polynomial will reduce, and then you can start over again, eliminate things from your list that are no longer possible, and then continue from that point. Now, when we're going to do the rational zeros also for that second one, and then we'll look at the rule of signs. So for our second example, our leading factors were factors of 4, and the final ones were 15. So for the second example, the final constant factors are 1, 3, 5, and 15, and the leading coefficient factors are 1, 2, twice, and 4. So our P over Q possible rational factors are, again, 1, everything in the top in the constant factors divided by 1. So 1, 3, 5, and 15. But now we also have to divide all of those by 2. So 1/2, 3 halves, 5 halves, and 15 halves. And then also divide everything by 4. So 1 over 4, 3 over 4, 5 over 4, and 15 over 4. Again, it's a lot to check when you have to do this by hand, but at least it is less than infinity. Another way that this rational zeros can be useful, you can use these ranges of zeros as a way to determine how big your graphing window needs to be. You know you can't have any zeros larger than your largest possible rational zero. So you can use that as sort of a starting point to make sure that you can actually see all the zeros and then narrow it from there. If you're using using technology, you know what the possible rational zeros are. So if you click on a 0 and you get some sort of crazy decimal, you know you only have to determine if it's one of these fractions and not something else. You don't have to worry about 13ths or anything like that in either of these cases. If you know that it's one of these rational expressions, then you know that that's one of your rational zeros. That gives you information about how you can then factor which zero to check. And then anything else that isn't on this list would be irrational. It would be something you would have to get from, let's say, the quadratic formula or something. All right, so now let's think about the rule of signs. Now, the rule of signs basically says that for a polynomial multiplied out, the number of sign changes is related to the number of positive real zeros. Now, in order to get the negative ones, replace x with negative x. And then do the same. Because now, anytime you had an x before, if it was positive, it's now negative, and anything that was negative is now positive in the resulting polynomial, and then the positive rule of signs will apply at that point. So let's start with our first example. Let's go back and grab them both. Now, for our first example, we want to count the number of sign changes. Boy, this keyboard suddenly is acting really weird. So count the number of sign changes. So we start out with a positive leading term. So now we have a negative term. So that's one sign change. It stays negative. So that's not a change. Now it flips from negative to positive. That's a sign change. So that's two. And then finally, we also have a positive term. So now that is staying positive. So there's two sign changes. So for the first one, there are two sign changes and two positive real zeros. Now, this can differ by negative 2k. Now, what I mean by that is like our turning points in functions, you can have, like if you have a fifth degree polynomial, you can have 4 turning points, or you can have 4 of them or 0 of them. So the numbers that are possible, this is the maximum number of positive real zeros, and they can go down by 2. So 2 or 0. But no more than 2. Now, if we try this with the negative zeros for the first one, we have to replace x with negative x. Now, essentially what that's going to do is that's going to flip all the signs of the odd terms, and the even terms will stay the same. So 3x to the 4th doesn't change because you put a negative in for negative x and raise it to an even power, it stays positive. But now our 11x cubed is going to become positive 11x cubed. And then negative x squared stays the same. 19 flips a sign, and then 24 stays the same. So now we're going to count our sign changes. It starts positive, no change. There's one sign change, stays negative, flips a sign again. So there are also two sign changes, and so two possible negative real zeros, or less by two at a time. So 2 or 0, basically. So if you had 5 sign changes in a really long expression, you would say you could have 5 or 3 or 1. Now for the second one, boy, for the second one, we're going to look up here. And again, what would our sign changes be? So starts positive, flips, that's one sign change, flips again, that's another sign change, flips again, that's another sign change, and then no sign change. So that's 3 possible positive real zeros. And then, so 3 or 1, 3 is the maximum. And then for the negative ones, we plug in negative x, and we would get 4x to the 4th doesn't change. The odd one changes. The even one stays the same. The odd one changes sign. And then the constant stays the same. So here there is only one sign change. So only one possible negative real zero. So for example, how do we combine these? Since there are more positive real zeros than there are negative real zeros, if I were trying to factor the second one, I would start by testing all the positive numbers before I started testing any of the negative values, because I'm probably more likely to run into, just by chance, a correct real zero. Rationals are real. They may not all be irrational. And so I'm probably more likely to run into a rational zero that's positive than one that's negative, because there are more positive zeros to find. And so this will give me, again, a little bit better chance of finding something that I can use to reduce the problem. And then I can go on and start with a smaller list of possibilities for the next round of things. So that is a sort of a strategic move rather than sort of part of the theorem, but that is a useful way of trying to combine the information from these two theorems so that you don't have to literally check everything. Because again, it's a long list, and doing it by hand, even with practice, is tedious. And if you tend to be prone to losing minus signs like I am, then it's a fraught process that you have to be really careful with. And there's no guarantee that you won't make a mistake and get something wrong. That's why we invented computers.